Hello viewers, in today's session we are going to discuss another important problem from integrals, and in this class we are going to evaluate this integral where we have 0 to infinity cos 3t minus cos t divided by t dt. So let us see how easily we can evaluate this integral using the concept of Laplace transform. So let us first quickly see the property of Laplace transform, which helps us to evaluate integrals of this kind, right? So let us first call this integral as I, and let us quickly see the statement of that property involving Laplace transform of a function, say f of t. Now let us consider a function, say f of t, right? And the Laplace transform of this function f of t is denoted by the usual notation, that is f of s, right? So now by the definition of a Laplace transform of a function f of t, we have the integral 0 to infinity e raised to minus s times t, and here we have f of t dt, right? So this is the notation for the Laplace transform of a function f of t, and this is the definition of Laplace transform of f of t, right? So now we have a very important property of Laplace transform, which helps us to evaluate integrals of this type. That is, if we have the integral, say 0 to infinity, and we have f of t divided by t dt, then this integral is equal to the integral 0 to infinity, and here we have f of x dx, right? So this is an important property that is related to the Laplace transform of a function f of t. So the integral 0 to infinity f of t divided by t dt is equal to the integral 0 to infinity and f of x dx. And here it is important to note that here we have capital F, and here we have the small f, right? So here we have small f, that is f of x, and here we have the capital F, that is f of t. So now let us come to the integrand, right? So here we have cos 3t minus cos t divided by t. So let us compare this expression with this one, that is f of t divided by t, right? So if we compare these two expressions, then we can easily see that the function f of t, that is capital F of t, may be taken as cosine 3t minus cos of t, right? So that the integrand cosine 3t minus cos t divided by t is of this form, that is f of t divided by t. So we can now take our function f of t as the difference of cosine 3t and cos t. So now our integral I takes this form, that is 0 to infinity, and cos 3t minus cos t over t may be taken as f of t divided by t dt, right? And now we can see that our integral I is of this form, and this integral is further equal to this integral, that is 0 to infinity and f of x dx. So now it implies that our integral I is now equal to this integral, that is 0 to infinity and f of x dx. And now f of x can be obtained by taking the Laplace transform of f of t, right? Because f of s, see, f of s is equal to the Laplace transform of f of t, and the function f of t is equal to cos 3t minus cos of t. And now by the linearity property of Laplace transform, we can write the Laplace transform of cos 3t minus the Laplace transform of cosine t. So now we know that the Laplace transform of cos at is given by s divided by s square plus a square, where s is greater than 0, right? So the formula for the Laplace transform of cosine at is given by s divided by s square plus a square, and here the Laplace transform of cosine 3t can be given as s divided by s square plus 3 square, because the value of a is 3. And then here we have only cosine t, that is cos 1t, so the value of a is 1 in this case. So we have s over s square plus 1 square. So we have s over s square plus 9 minus s divided by s square plus 1. So now the Laplace transform of f of t is given by f of s, and f of s is a function of s, that is s over s square plus 9 minus s divided by s square plus 1, right? And f of x can be written with the help of this expression by replacing s by x, right? So replacing this s by x, we can now write f of x, that is x divided by x square plus 9 minus x over x square plus 1. So now let us substitute this value of f of x in this integral, and this integral is given by our original integral, that is I. So now I can be given by 0 to infinity, and for f of x we have x over x square plus 9 minus x divided by x square plus 1 dx. So now we have to evaluate these two integrals, and these two integrals are simple integrals, because we can transform these two integrals into this form, that is f prime of x divided by f of x dx. So whenever we have an integrand of this type, when the derivative of the denominator it exists in the numerator, then this is simply the natural log of f of x. So here we have the first integral, so we can now write 0 to infinity, and here we have x, so let us write it as 2x, and here multiply this integral with half, so that this 2 and this 2 get cancelled, and we have now again half and 0 to infinity, and here also we can write 2x divided by x square plus 1 dx. Now the derivative of x square plus 9 is 2x, and the derivative of x square plus 1 is 2x. So that's why we have divided and multiplied this integrand by 2, right? And similar is the case with this one. So now we have half, and the value of this integral is now given by natural log of x square plus 9 due to this result. And then we can take half common, and here we have natural log of x square plus 1, and the limits of integration are from 0 to infinity. So using the properties of log, we can now write natural log of x square plus 9 divided by x square plus 1. And here the limits of integration are from 0 to infinity. And here we have used this result, that is log of a minus log of b is equal to log of a divided by b, right? So now we have to evaluate this expression for the upper limit and the lower limit, and then we'll take the difference. So now I can be written as half, and we can now write natural log. And here we can also express this rational expression, that is x square plus 9 divided by x square plus 1, like this. Taking x square common, we have 1 plus 9 divided by x square, and in the denominator also we can write x square and 1 plus 1 over x square, right? And here the limits of integration are from 0 to infinity. Now this x square and this x square get cancelled. We have half, and natural log of 1 plus 9 over x square divided by 1 plus 1 over x square, right? Okay, so now when we take x tending to infinity, right? So when x tends to infinity, then 1 over x square, it tends to 0, right? So when we take the upper limit, that is x tending to infinity, then 1 over x square tends to 0. So this expression is 0, and this expression is also 0. So we have half, and then we have natural log of 1 plus 0 over 1 plus 0, right? And when we take x is equal to 0, then we have here, see, this expression is obtained from this one, right? That is x square plus 9 divided by x square plus 1. So when x is equal to 0, then here we have 0, that is 0 square is 0. Then we have 9, and here also we have 0, and this is plus 1, right? So let us simplify it. So we have half, and then we have natural log of 1. 1 plus 0 is 1, 1 plus 0 is 1, so 1 over 1 is 1. And then we have natural log of 9, because this is 0 plus 9 is 9, 9 over 1 is 9. So we have half, natural log of 1 is 0, and natural log of 9 can be written as natural log of 3 square. So we can now write I is equal to half, and we have minus 2 times natural log of 3. So now this 2 and this 2 get cancelled, and the value of this integral I is equal to negative of natural log of 3. Hello viewers, in today's session we are going to discuss another important problem from integrals. And in this session we are going to evaluate this important integral with the help of the concept of beta and gamma functions, right? So here we have to find out the value of this integral from 0 to 1, and the integrand is x raised to 8 multiplied with 1 minus x cube raised to 7, and here we have dx, right? So let us see how easily we can solve this integral with the help of some important results from beta and gamma functions. So let us first make use of the concept of substitution method. So let us substitute here. X cube is equal to say t, right? So let us call this integral as I, and let us take x cube is equal to t, so that we can write x is equal to t raised to 1 by 3. So what we have done here, we are making this substitution x cube is equal to t in order to convert this integral into the beta function, and the beta function is defined like this, that is beta m comma n is given by this integral, that is 0 to 1 t raised to m minus 1 and 1 minus t raised to n minus 1 dt, where m and n are both greater than 0, right? So x is equal to t raised to 1 by 3. So let us differentiate x with respect to t. So we have dx over dt is equal to d by dt of t raised to 1 by 3, and using the power rule here, that is d by dx of x raised to n is nx n minus 1. So here n is 1 by 3, so we have 1 over 3 t raised to 1 by 3 minus 1, that is 1 over 3, and t raised to minus 2 by 3. So dx can now be written as 1 over 3 t raised to minus 2 by 3 dt, right? Okay, now here the limits of integration vary from 0 to 1. So let us change the limits accordingly. So when x is 0, 0 is our lower limit. So the value of t can be obtained from this relation. So t is 0 cube, that is equal to 0. And when x is equal to 1, 1 is the upper limit, then the value of t can again be calculated from this relation. So we have 1 cube, that is equal to 1. So we can see that when x varies from 0 to 1, t also varies from 0 to 1. So the limits remains the same. So we can now write I is equal to 0 to 1. Here we have t is equal to 0. Here we have t is equal to 1. And x can be replaced by t raised to 1 by 3. So we have t raised to 1 by 3, and here the exponent is 8. Then we have 1 minus t because x cube is t, and then we have the exponent 7, and dx is given by 1 over 3 t raised to minus 2 by 3 and dt, right? So let us simplify this expression. So we can now write I, and we can take 1 by 3 outside the integral. We have 0 to 1, and here we have t raised to 8 by 3, and then we have t raised to minus 2 by 3. So adding these two exponents, so here we have plus minus 2 by 3, and then we have 1 minus t raised to 7 and dt. So now we can write 1 by 3, 0 to 1, and t raised to 8 by 3 minus 2 by 3 is 8 minus 2 over 3, that is 6 over 3. So here we have 2. So here we can write t square, and here we have 1 minus t raised to 7, and here we have dt, right? Okay, so now we can write 1 over 3, 0 to 1. Now t square can be written as t raised to 3 minus 1. And here we have 1 minus t raised to 7. 7 can be written as 8 minus 1 dt. So now we can see that this integral is of this form. So here 0 to 1, 0 to 1, then we have t raised to m minus 1. So here the value of m is 3, and here we have 1 minus t, 1 minus t, and n minus 1, and the value of n is 8. So m is 3 and n is 8. So this integral is now given by the beta function, that is beta of m comma n. M is 3 and n is 8. So now we can calculate the value of this beta function by using the relationship between the beta function and gamma function. So beta m comma n is given by gamma m, and gamma n divided by gamma n plus n, right? So here we have 1 over 3, then we have gamma 3, then we have gamma 8 divided by gamma 3 plus 8, right? So now we can use another result, that is gamma n plus 1 is equal to n factorial, right? And here gamma 3 plus 8 is equal to gamma 11. So we can now write 1 over 3. Now gamma 3 can be written as uh, that is 2 plus 1, gamma of 2 plus 1, that is equal to 2 factorial, that is 2 times 1, that is equal to 2. So here we have 2, and then gamma 8 can be written as gamma 7 plus 1, that is equal to 7 factorial. So here we have 7 factorial, and then we have gamma 11. So gamma 11 can be written as gamma 10 plus 1, that is equal to 10 factorial. So here we have 10 factorial. So now we can simplify these numbers. So we have 1 over 3, 2, and here we have 7 factorial, and 10 factorial can be written as 10 times 9 times 8 times 7 factorial. So here 7 factorial and 7 factorial get cancelled, and here 2 times 4 is 8. So we can now write the value of the integral I as 1 over 3 times, here we have 1 over 10 times 9 times 4, right? So this is equal to 1 over the product of these four numbers. So here we have 30, 3 times 10, and here we have 9 times 4, that is 36. So the product of 30 and 36 is given by 3 times 6 is 8, 3 times 3 is 9, and 9 plus 1 is 10. So we have 1080, right? So here's the value of this integral I is given by 1 over 1080. So this is how, by the concept of beta and gamma functions, we can easily evaluate these kind of integrals. Hello viewers, in today's session we are going to discuss another important integral using the concept of beta and gamma functions, right? So here we are going to find out the value of this integral, that is from 0 to infinity, and we have x divided by 1 plus x raised to 8 dx, right? So here we'll solve this integral using some concepts from beta and gamma functions. So let us start. So let us call this integral as I. So first of all, we'll make use of the method of substitution, right? So let us here substitute, say t is equal to x raised to 8. So the first step in solving this integral is to make this substitution so that we can transform this integral into the beta function, right? So t is equal to x raised to 8, so that x is equal to t raised to 1 over 8, right? Now let us differentiate both sides with respect to t. So we have dx over dt is equal to d by dt of t raised to 1 over 8. And using this power rule, that is the derivative of x raised to n with respect to x is nx n minus 1. So here the value of n is 1 over 8, so we have 1 over 8. Then we have t 1 over 8 minus 1, so we can now write 1 over 8 t raised to minus 7 over 8, right? So now dx can be written as 1 over 8 t raised to minus 7 over 8. And here we have dt. So now here the limits of integration are 0 to infinity. So when x is equal to 0, that is the lower limit, then the value of t can be obtained by taking x is equal to 0 over here. So 0 raised to 8 is 0, and the upper limit is infinity. So when x tends to infinity, then obviously t also tends to infinity. So now let us write this integral in terms of the variable t. So we can now write 0 to infinity, and for x we can now write t raised to 1 over 8. And for dx we can now write 1 over 8 t raised to minus 7 over 8. And here we have dt, and in the denominator we have 1 plus x raised to 8. So we can now write simply 1 plus t. So now let us rearrange the terms. So we have I equal to 0 to infinity. We can take 1 over 8 outside the integral, and we have t raised to 1 over 8. And here we have t raised to minus 7 by 8. So we can add these two exponents. So we have here a minus 7 over 8. And here we have dt, and in the denominator we have 1 plus t raised to 1, right? Because we can write 1 plus t as 1 plus t raised to 1. So we can now have 1 over 8, 0 to infinity, and t raised to 1 minus 7 is here we can write 1 minus 7 over 8, taking 8 as LCM. So we have minus 6 over 8. So this is minus 3 over 4. So we can now write minus 3 over 4 and 1 plus t raised to 1, and here we have dt. So let us now convert this integral into the beta function. So now the beta function is defined like this, that is beta m comma n is given by the integral 0 to infinity. And if we take the variable as t, then we have t raised to m minus 1 divided by 1 plus t raised to m plus n, right? So the beta function is defined like this. So if we compare this integral with this one, right, then here we have minus 3 over 4, and here we have m minus 1. So here our aim is to find out the values of m and n. So comparing this integral with this one, leaving 1 over 8, so we have m minus 1 is equal to minus 3 over 4, and m plus n is equal to 1. So we have two equations. So from this we can now write m is equal to minus 3 by 4 plus 1. So m is minus 3 plus 4 over 4, that is 1 over 4. And taking m is equal to 1 over 4 in this equation, we have 1 by 4 plus n is equal to 1. So n is 1 minus 1 by 4, that is 4 minus 1 over 4, that is 3 over 4. So now m is 1 over 4 and n is 3 over 4. So now we can write this integral as 0 to infinity and t raised to minus 3 over 4. Now minus 3 over 4 is m minus 1 and m is 1 over 4. So we can now write 1 over 4 minus 1, and here we have 1 plus t raised to 1, and 1 is equal to m plus n. So m is 1 over 4 and n is 3 over 4, right? So this is how we can express this integral in terms of beta function, right? Okay, so now we have 1 over 8 and this integral is now equal to beta of 1 by 4 comma 3 by 4. M is 1 over 4 and n is 3 over 4. Now here to get the value of beta m comma n, we can utilize one important result which connects beta function and gamma function. So we have gamma of m, then we have gamma of n divided by gamma m plus n. So here we have 1 over 8, gamma of 1 by 4, gamma of 3 by 4 divided by gamma of 1 by 4 plus 3 by 4. So let us simplify this expression. We have gamma 1 by 4 and gamma 3 by 4. And in the denominator we have 1 because this is gamma. 1 by 4 plus 3 by 4 is 1 and gamma of 1 is 1. So in the denominator we have 1. Now we have this expression, and to get the value of this expression we have to make use of Euler's reflection formula, which goes like this. That is gamma n gamma 1 minus n is given by pi divided by a sine of n pi, right? And if we take n is equal to 1 by 4 in this result, then we have gamma of 1 by 4, gamma of 1 minus 1 by 4, that is 3 by 4, is equal to pi divided by sine n pi. N is 1 by 4, so here we have pi over 4. So this is pi divided by sine 45 degrees is 1 over root 2, and we can take root 2 to the numerator. So we have pi times square root of 2. So substituting the value of this expression as pi times square root of 2, we have 1 over 8 times pi root 2. So this is pi root 2 over 8. So viewers, the value of this integral I is equal to pi times square root of 2 divided by 8.